we are discussing memory organization. We have seen the characteristics of some memories, both internal and external. Let us visit the last slide to start our discussion, where the characteristics of the different memories have been summarized. See, here we have that different memories. Here's the CPU registers, memory, that SRAM, main memory, the DRAM, the disk, and the tape. We have summarized the different aspects. Here is access type, cost per megabyte, and the capacity in terms of bytes. Okay. Now, in the case of registers, naturally the access type is random. Access time is 1 to 3 nanosecond. Cost per megabyte is high. Okay, and the capacity is say from 64 to 1024. Okay. Now, in the case of an SRAM, the access type is once more random. Access time is 5 to 25 nanosecond. The cost is somewhat high, $100 to $200, and the capacity generally is 256 kilobytes onwards. Okay, in the case special applications where we put it. Okay. In the case of a DRAM, the access type is random once more. Access time is 60 to 120 nanosecond, a bit a bit slow. The cost per megabyte is $5 to $10, somewhat low, definitely. And the sizes are generally 16 megabyte onwards. Nowadays, since the cost is low, the simple PCs can have even 64 megabyte, and the servers can have much more memory. The main memory, because the cost is low, okay, and the access time is somewhat tolerable, okay, the main memory is constructed out of DRAM. Now here is a disk. The access type is direct. The access time is 10 to 20 millisecond, pretty high. Cost, of course, is pretty low, and the capacity generally that is used is from 8 gigabytes onwards. Okay, it can be several, at least 100 or more gigabytes even, right? Now the tape, the access type is sequential. The access time is pretty high, 20 millisecond to 10 second. Okay, the cost per megabyte is very low, and the capacity can be 1 terabyte onwards. Okay, but generally this tape is used as a backup of the disk, as an archive. Okay. Now let us see that, as I said, that because the cost here is low, access time is tolerable. Okay, the main memory is generally constructed of the DRAM, right? But if we could make the main memory out of SRAM, right, where the cost per megabyte is somewhat high, 100 to 200, okay, it will be pretty costly, but naturally the access time will be very low, and therefore you see the execution of the program will be quite fast. Now let us see in terms of these characteristics, one feature that I would like to show you, that is this, that if we draw the access time versus the cost, okay, the curve somewhat looks like this. Here the scales are logarithmic, both in cost as well as in terms of the access time. Now here lies the static RAM region. Here is the dynamic RAM region, the magnetic disk, CD-ROM, and the magnetic tape. Therefore, the more or less the access time versus cost characteristic is depicted by means of the straight line AB. And if you study it, you will see that if you want to decrease the access time by a factor of 10, okay, the cost increases by about 100 times. However, this as well as this is a picture as stands at the end of 1999. Naturally, 4 years since hence, okay, the total picture will change. right? Because of the rapid advances that takes place in the semiconductor technology. Now it's coming back over to here. We'd be pretty glad if we could make a main memory of the SRAM because of this situation. Say that if we have to have an access and if the memory is slow, so for example the CPU wants to, as this slide they showed earlier, the CPU wants to say read something from the main memory, the address bus is activated, the memory read is activated, okay, the moment the memory read is activated, now the address bus carries the address and the memory read signal, the control bus carries it, okay. But you see, because the memory is pretty slow, the data read comes after several cycles, okay, after the memory read request has been put high over here, and that this number of cycles depend upon how fast the memory is. The slower the memory, the number of timing states will increase, and therefore the execution time of the program will automatically decrease. Okay. Therefore, it is very desirable that we have main memory of fast access, okay, fast access time. That is, it's desirable that if we could make the main memory of the static RAM only, but the cost prevents, right? Therefore, can we have something that where can we try to make an arrangement that where we will have the access time of the SRAM, okay, but we'll be able to afford the capacity of the DRAM. That is possible by an arrangement, we call it cache memory. What is done is that, let's say, portion of the main memory, the portion of the main memory where the program lies, that means a part of the program, if we transfer it to this SRAM, okay, right, then if the CPU starts executing that portion of the program from this SRAM, then the access will be pretty fast and the CPU will execute this program quite fast. When we'll find that when either the program or the data that has been transferred from the main memory into this memory, okay, is not there, then only the CPU goes to the main memory and fetches the either the instruction or the data. Okay, in such situation, we call this memory as cache memory. The meaning of cache, the dictionary meaning of cache, is a safe place for hiding or storing things. This is the situation as if that we are storing some part of the program in the cache memory. We are the CPUs trying to access the program or the data from the cache as far as it is practicable and as long as it is there. If it is not there, then the CPU goes to the main memory to fetch either the instructions or the data. Now, this way, if most of the times we find that the instruction or the data is in the cache memory, then you can see that we can approach the access time of the SRAM, and since the major portion of my program or the data is in the main memory and I am transferring only a part into the cache may be relatively smaller and the main memory may be much higher, and therefore essentially we can have a very high capacity main memory. That is in fact the arrangement that is done in the case of cache memory management system. Now the question therefore arises that whether that is possible or not. By that I mean that whether we can keep portions of the program and data in the in the cache memory, okay, and try to execute the program, whether how much successful it will be. Now that will be quite possible because of the principle of locality. Okay, the principle of locality is two types. One is a temporal locality Another is called the spatial locality. Okay, the temporal locality is essentially the locality in time. It means that if an item is referenced, it will tend to be referenced again soon. Here an item is either a program, either an instruction in a program or a data. Okay. For temporal locality, the locality in time says, let me repeat once more, that if an item is referenced, it will tend to be referenced again soon. Okay, and the spatial locality says, which is the locality in space, it says that if an item is referenced, items whose addresses are close by will tend to be referenced soon. Okay, therefore this is the spatial locality, and because the temporal locality and the spatial locality holds in the programs in general, that it is possible that we can bring a small portion of the program from the main memory into the cache and try to execute the program, keeping that portion in the cache. Okay. Now let's see why it is generally possible. Suppose that, say if we have a loop, like say for I is equal to 0, say I less than n, I plus plus, okay. And here, say I am simply adding the elements up to one-dimensional array, okay. Now see, this, when it will be translated into machine language program, will be translated into several instructions like this. Right. Now, if you examine any program, you will find that the major time that is needed in executing any program lies in the loops. Okay. The sequential control is executed very fast, but the loop control is executed. Since the loop is executed many times, the major portion of the time that is taken for execution of any program lies in their loops. Okay. For example, in this loop, this instruction into which this statement, high-level language statement, will be translated, will be executed n times. Now, which means that if a particular instruction, this instruction is executed now, there is a high probability that this instruction will be executed very soon because it is in a loop. This is in fact the temporal locality. Now the spatial locality says that if this instruction is executed, the instructions which are close by, say this one, this one, this one, this one, will be executed pretty soon. Okay, that is the spatial locality. That if an item is referenced, items whose addresses are close by will tend to be referenced soon. So because of both this temporal locality and the spatial locality, it is quite viable that portions of the program can be taken into the cache memory and can be executed. Okay. Now, say you can see that we can have another example just to convince you that most of the time the program executes loop. Okay, for say I equal to 0, say I less than n1, I plus plus, say for j is equal to 0, say j less than n2, j plus plus, say for k is equal to 0, k less than n3, k plus plus, and say we have the loop body here. Then whatever are the instructions here, this innermost loop will be executed in 1 into n2 into n3 times. And you see that immediately that the locality concept turns out to be applicable very strongly, right? Now, with this in mind, let us see that how that cache organizations can be implemented. Okay. Here we are trying to show the implementation of a cache organization which we call the direct mapping cache. You know that since you have to bring a portion of that main memory's content into the cache memory, some kind of mapping has to be done between the main memory and the cache memory. Okay. Now, let us see that here what we have, let's take an example, okay, a concrete example to show this mapping. Say here we have taken the address of the computer, right? Let's assume that it's a 24-bit address, that means from 0 to 23, right? Which means essentially it is 16 megabyte that this address can, addressing can be done, 16 megabyte. Now, we assume that every byte is accessible, also a word that is consisting of 4 bytes that is also accessible, right? That means generally what I want to mean is that generally the computer will try to access one word consisting of 4 bytes, okay? But if necessary, every byte is accessible, that means every byte can be read. In that situation, the main memory here had been shown to be a 4 mega word. Each 4 byte word is called a block, say block B. This is our cache memory, okay. This is our cache memory. And say this is of size, we say M. Here we have taken M to be 16K, therefore the addresses of the cache can be from 0 to 16K minus 1. Each location of the cache is called a line. Our mapping will map one block of main memory into one line of the cache. And the mapping function in the case of a direct mapping cache that we employ is, if B is the block address, that means if B is this 22 block address, 22-bit address, okay, I am leaving aside this one. If B is this 22-bit address, then the L, that means that mapping address L is given by B mod M, where M in this particular case is 16K. If this be the general mapping in the case of a direct mapping cache, where M is the cache size, B is the word address, okay, then B mod M, the address that we get, L, is the address where that particular block will be mapped into the cache. If this be the mapping that is employed, then what happens is, this is the mapping we get. That means 0th address of the word, 0th word, mth word, twice mth word, all of them will map into the 0th line of the cache. First word, m plus 1 word, twice m plus 1 word will map into the first line of the cache, and so on, that m minus 1 word, twice m minus 1 word, okay, all of them will map into the m minus 1 line of the cache. Now, keeping this in mind, let us see that if we take this word address and let us divide this word address, okay, into 14-bit here, 2 to 15, okay, 14-bit here, which we call that index, right? This 14-bit accounts for this 16K, okay, addresses, and then another 8 bits here from 16 to 23, okay, which we call tag. Therefore, the complete word address is divided into 2 parts. One we call that index, consisting of 14 bits. Another is the tag field, which consisting of the 8 bits. Then this 14 bits address, if we take, right, this 14-bit address will essentially determine the location of a particular word within a segment that is decided by the tag field. By that, let us see, so for example, this tag can be from 0 to 255, therefore 256 values can be there in that tag. Each tag determines one memory segment. For example, this is the 08 memory segment, right? Then this next one will be the first memory segment. That way, for example, this one is a kth memory segment. In any such kth memory segment, this index determines the offset of a particular block from the beginning of that segment, right? And that is determined by this. Now, when I say that this is the mapping, that means B mod M, then this offset L determines that this particular block will be mapped into this cache, where this cache size we keep same as this segment size. That means this is the segment size determined by the number of bits over to here. Since this is 14 bit, this is 16k word. This cache is also 16k word. This index determines the offset L, okay, when you take that B mod M, and therefore that offset directly, that means this block directly is mapped into the 11th line of the cache. This is the mapping that is done, and that is exactly what we have been telling, that 0 m twice m will map to 0, okay, 1 m plus 1 twice m plus 1 will map to 1, right? Since therefore a block which is in the same relative position of any segment of the memory will map into the same relative position within the cache. Okay. Now with this mapping, therefore, let us see that what we'll have to do. Right. First thing is that, say if this block's content has been transferred in this cache here, right? Now you see, if we just leave aside this portion, right? If this block's content is here, then there's no way of knowing that this content is of this particular block, or say this particular block, okay, which is also that at an offset L from the beginning of the 0th block. Therefore, when we have transferred a word or a block from the main memory into the line of the cache, okay, at the same time we'll have to tell that which particular segments block has been transferred into, and that is determined by the tag field in that address field, and that tag field in when we are copying this block into the line of the cache, that tag field is also copied over to here. That means if we are copying the bth block, okay, which falls at an offset of L in that kth segment, then that k is put over to here, and that content, say for example that x, will be put over to here. That x consists of 4 bytes. Okay. This in fact is a mapping that is done between the main memory and the cache memory. Now let us see, with this thing explained, let us see that how do we go about that cache addressing, okay, or generally the memory addressing. The entire picture has been redrawn here. This in fact is the complete address, the 24-bit address. From here to here is the word of the block address. This is the cache divided into 2 parts. One is a 32-bit content, okay. This contains the tag field, okay. And here we keep another bit we call the valid bit, okay. What is the purpose of this valid bit? We'll explain. What happens is that when the address is obtained by the CPU, okay, the CPU takes this 14-bit as the address in the cache memory, and it comes into that cache memory. When it comes to the cache memory, then it has to see whether the tag bit, right, is matching with the B's tag bit or not, that address's tag bit or not, to find this, to know that which particular block's content is here, right? To do that, what it does is that this tag bit is taken, the tag bit that is stored over here, is taken from that cache, right, that is compared, and if this comparison turns out to be that it is equal and the valid bit is 1, in that case it says that it is a hit. That means the required word that this address is trying to point to is in the cache. That is our hit. Okay, if it is a hit, then we can take that entire word out of this cache memory, or if we need a byte, this gives a byte offset. Okay, therefore these 2 bits can be taken and these bytes can be put into the multiplexer, and the corresponding byte, depending upon the value of this input, the corresponding byte can be taken out. Either you can use a mux or you can use this as an offset, okay, to determine that which particular byte you want to take out. Right. Now this is the way that cache addressing is done. Now let us see how actually the entire thing goes. Actually, before that, let's say that if it is not a hit, right, if it is a miss, in that case it says that the content of the block, okay, or the memory location this address is pointing to is not in the cache, therefore it is a miss. And if it is a miss, then the CPU has to go to the main memory to fetch the content of that particular word. Okay, now which means that the moment it is a miss, it is a penalty. The penalty is that you have already have spent, say, T1 time that is needed to access this cache memory, and you have to now spend the T2 time, that is the access time that is needed to access the main memory. Therefore the total time needed is T1 plus T2. Okay, therefore either it is a hit or it's a miss. If it is a hit, then we get it here in the cache. If it's a miss, then we go to the main memory to fetch the content of that particular block. Okay. Now let us see that how the entire thing goes. To start with, the cache naturally contains a garbage. All the valid bits are put to 0. Okay. And say an address is thrown by the CPU. The corresponding block is taken from the main memory, is loaded into the cache memory. The tag bill corresponding tag field is taken and is loaded into the tag field of the cache memory, and the valid bit is made 1. This way, after some time, because of the locality, we'll find that most of the memory locations whose content is needed here, that is available in the cache, and therefore most of the time we'll have a hit. Right? And this hit, because of this hit, okay, the percentage of hit being high, we'll be able to access the data from the cache memory, access the data or the instruction, whatever it is, from the cache memory directly. Okay. Now you see one thing, that when I was talking about instructions and data many times, you see that this is a situation of an instruction that the temporal locality or the spatial locality holds, right? Similarly, you see that the temporal locality and the spatial locality will hold for the data A, B, and C also, because mostly, naturally, that say the A array, that B array, and say the C array, okay, say A array, B array, and C array, these are accessed sequentially, and therefore if a data is taken, it is expected the data, the spatial locality, that it is expected that the data nearby will be accessed immediately. Okay. Similarly, if this data is taken, okay, the data from the array B is taken, this data is taken, then it is expected that nearby data will be accessed very soon, and so for C. Okay, therefore, both the temporal locality as well as the spatial locality, and here more spatial locality will hold in the case of this data. Therefore, when I'm saying that, I am talking about that information is available mostly in the cache. Okay, what I mean that either it may be instructions or maybe data that will be available, and the chances that the hit percentage is high will be true because of these two localities, right? Now let us see in these terms what will be our gain, okay, how much we gain, okay. But before that, let me remind once more that this we call is a direct mapping cache, okay, because a particular block is mapped into a particular line of the cache, okay, depending upon the formula that have been given. If it's a 1, 2 for a particular block, this is essentially a particular block is mapped into a particular line of the cache. Okay, and as I told you that since the mapping maybe here it is because of the mod operations, because of this mod operation, you know that these blocks which are in the same relative positions in the segment will be mapped into the same line, and that sometimes create a problem. What's the problem that is created? We'll see. Now let us see now what's the advantage that we get. Okay, here we have shown that the access time versus the percentage hit. Okay, now say the percentage hit is 20%, 40%, and so on over to here. The access time is, say, shown over to here. Let us assume that access time for the cache memory T1 is 10 nanosecond, and the access time, which is a typical figure for the SRAM, and access time for the main memory is T2, that means 100 nanosecond, which is a typical figure for the DRAM. Now, if the access time, if the hit ratio is 100%, then you will always get it in the, if the hit ratio is 100%, then you will always get that information in the cache, and therefore the access time will be 10, the access time of T1. Now the hit ratio is 0, then all the time we are missing it in the cache, okay, and therefore we'll have to go into the main memory, right, and then we'll have to get the access in the main memory. Let us see what happens when we miss. So for example, when we miss, we go to the main memory to fetch the information, that is instructions for the data. When we fetch it, we load the content of that main memory into the corresponding position in the cache. The tag we put over to here, and also it is sent over to the CPU so that the CPU can go ahead with that information. Right? Therefore, in the case of a miss, not only that we access it from the main memory, as we access it, we replace the previous content of the cache memory by this present content of the main memory along with its tag. Okay, that is a replacement it goes. Right? Therefore, you see, if it is a miss, then the total time that is needed is T1 plus T2, because we first searched in the main cache memory and then in the main memory. Therefore, this line, the red line, depicts the behavior of the access time in terms of the percentage hit. Now, if the percentage hit is 90%, which is typically a figure, 90%, then you see that the access time that we get is 20, which is very close to the access time of the cache memory. And see, in this case, we have taken that for 16K is the cache memory in this particular example. Okay, 16K as a cache memory and 16 megabyte as the main memory. Okay, or 16K word as the cache memory, or 4 mega word as the main memory. Now, since the cost of the total system, that means the cache memory and the main memory, will be M1 into C1 plus M2 into C2 divided by M1 plus M2, which is, well, M1 is the size of the cache, C1 is the cost of the cache, M2 is the size of the main memory, C2 is the cost of the main memory. Okay, and since M2 is much greater than M1, you see the cost C will very nearly equal to, okay, will be C2, which means that we are getting an access time which is close to T1, the access time of the cache memory, at a cost which is close to C2, the cost of the main memory. Okay, which that way our purpose is served. By that we wanted to have a fast access, okay, good amount of, okay, good capacity of the main memory that is served by means of this cache. Right? And as I said, that getting a 90% hit is very usual, okay, with a good amount of cache memory that we can afford. Right? Now let us see what are the disadvantages of the advantages and disadvantages of the this direct mapping. The direct mapping cache organization's advantages is simple and inexpensive to implement. Okay, since the mapping is very simple, and naturally this mapping has to be done essentially by means of the hardware for the fastness. Okay, if it is, since it's simple, therefore it is inexpensive. Okay, but there is a disadvantage. The disadvantage is that since it's a fixed cache location for any block, okay, as we have been telling, that it's a fixed cache location for any block, for this block, all of them are mapped into the same cache location, right? This creates a disadvantage. Because suppose that your instruction that is being executed is in these blocks, okay, or the blocks in the vicinity of it, and the data that are these instructions are executing with are in the vicinity of these blocks, okay, then since both this block and this block will be mapped to the same line of the cache, actually when this block is here, this block cannot be there, it will push out this block, and when this block will be there, it will push out this block. Immediately you see that the hit ratio falls like anything, and that will be true if the two data, that means say the data that are these instructions are dealing with are in blocks which maps into the same line of the cache memory. In that case, that the hit ratio will immediately fall, and therefore the performance will decrease. Therefore, let's see that what we have obtained here in this direct mapping of the cache and the implementation of this cache. By cache, we are getting a fast access, okay, but at the cost of DRAM, okay, at the cost of the main memory. A mapping has to be involved. We have just explained one direct mapping cache, and the direct mapping cache memory, we are getting a simple and inexpensive mapping from the main memory into the cache memory. But there is some disadvantage that since the blocks fixed are mapped into the fixed block, fixed cache, okay, the hit ratio, depending upon the situation, may fall down. Therefore, we'll see in the next lecture that how this can be improved, okay, that is how we can have a different kind of mapping where this situation may improve.